Hello, this is Mrs. Taylor, and I'm going to introduce you to the idea of differentiability. And differentiability and continuity go hand in hand. So first we'll look at just differentiability, and then we'll move on to how it is related to continuity. So to start with, a function will not have a derivative at a point if the derivative from the left and the derivative from the right do not approach the same value. So remember, a derivative is a limit, and therefore you can have a left and a right hand limit. So what we have here is basically the setup for the formal definition of a derivative. It's just approaching a value from the left here and from the right here. So visually, graphically, what this looks like is that I have four types of instances where if you are looking at a graph, you will know that the derivative fails to exist. So for the first case here, it's a corner, and remember, derivative is just slope. So you can think of this as a situation where approaching from the left of x equals 0, I have a negative slope, and from the right is from x equals 0, that slope is going to be positive. So if at x equals 0, to the left my derivative will be negative because the slope is negative, and from the right my derivative will be positive, there's no way that those left and right hand limits could equal. So a corner is a place where a derivative does not exist. So we would say that this function here is not differentiable at x equals 0. For the second situation, we have a cusp, and it's pretty much the same situation as the corner. It's just instead of just being two straight lines, we have these curves here. So we call it a cusp instead of corner. Same situation though. Approaching from the left, I would have a negative slope. Approaching from the right, it's a positive slope. So at x equals 0, there would be no derivative. I would say it's not differentiable at x equals 0. Number 3, that situation is a vertical tangent line. And remember, a vertical line has an undefined slope. It means 0 on the bottom. So that would be why we wouldn't have a derivative there, because the slope itself would be undefined because it's a vertical line. And then number 4, this is a situation where we're going to have a little more difficult time understanding exactly how this one works as not differentiable, because if I look at it, if we think in terms of slope, from the left of x equals 0, the slope is 0, and from the right as x approaches 0, the slope is 0. So you could argue that the left-handed and right-handed slope are actually the same. However, let's go back to the original setup. So it's f of x minus f of c over x minus c. So let's look at that in more detail here in our number 4 scenario. So our c value is where we're thinking it's it's not differentiable. So we would say the limit as x approaches 0 from the left of f of x minus f of 0, our c value, over x minus our c value, which is 0. So f of x, as it approaches 0 from the left, takes on the value of negative 1. And then f of 0, the actual value this function is defined at, is positive 1. So when I plug in those values, I get negative 1 minus 1 over, and then x is 0, so 0 minus 0, which is 0. And I just realized that when you plug in values, you don't use the limit notation, so let me clean that up. Alright, and so what I'm looking at here is I'm looking at a constant over 0, which when we get that situation with limits, that indicates the limit does not exist. So in this case, a discontinuity would put us in a position where we have a non-existent limit. So even though visually we could argue the slopes are the same, by definition, using the limit format, we find out that actually the derivative does not exist at a discontinuity because our limits may not exist, either from the left or right or both. So bottom line is a function is not differentiable at a corner, a cusp, a vertical tangent, and a discontinuity. Let's look at an example problem. So this problem, it says compare the right hand and left hand derivatives to show that the function is not differentiable at the point P. Find all points where f is not differentiable. So using these left and right hand limits for our left and right hand derivatives, we can analyze this situation here to find the point where it's not differentiable and support it mathematically. Visually, I can see that it's not going to be differentiable at x equals 0 because it's, I guess you call that a cusp or a corner. But we need to support it with some algebraically. So let's look. The limit as x approaches c from the left, where c value is going to be 0. And from the left, my function is x squared. So I'm going to write this out using x squared instead of f of x. And then f of c, well, f of 0 is 0 over x minus c, which was 0. So simplify, and x squared over x divides out to just be x. Plug in your 0 and you get 0. And then over here, from the right, if I write it out, the limit as x approaches 0 from the right, the function from the right would be x minus f of c. F of 0 for this graph is 0 over x minus c, x minus the c value, which is 0. And so x over x divides out to equal 1, and since it's a constant, the limit would be 1. So I could see clearly that my left-hand derivative and my right-hand derivative are not equivalent, therefore it is not differentiable at the point P. So not differentiable at P. And so not only have I arrived at the conclusion I knew I would arrive at, but I've supported it algebraically. I have proof. Okay? So that is one type of problem we're looking at with differentiability. The other one is going to work with continuity. So first we need to make sure that we're all aware that differentiability implies continuity. So remember earlier, one of the graphs where we knew that the derivative would fail to exist is when we had a discontinuity. So therefore, if a derivative exists, it has to be continuous. So if f has a derivative at x equals a, then f is continuous at x equals a. So what that means is if I know the derivative exists for a function, then I know it's continuous, and I can draw that conclusion every time. Graphically, you may be asked to do something like this. So it says the graph of a function over a closed interval D is given. At what domain points does the function appear to be differentiable? Continuous but not differentiable, neither continuous nor differentiable. So those are three different scenarios, and for number 5, it's just a linear function, and from -3 to 2, it's continuous on the entire interval, and there are no cusps, corners, vertical tangents, or discontinuities. So on what values is it differentiable? Well, that's the entire thing. So from -3 to 2. And for B, it's continuous but not differentiable. We just said it's differentiable in the entire interval, so there are none. And then neither continuous nor differentiable, well, again, none. Now let's look at one that's actually a little more interesting. So in this one, it's the same set of directions, but the graph is much different. So on what domain points is this function, is this function a differentiable? And so if I look at the graph, I see that I have a corner at x equals -1. I have a discontinuity at x equals 0 and a discontinuity at x equals 2. So I can break this up into intervals, or I could say that it's differentiable at all points in the interval -2 to 3, except those x values we just said. So x equals -1, 0, and 2. Alright, so in the next question here, they want to know where it's continuous but not differentiable. So if I look here at the 3 points we just said that it was not differentiable, at x equals -1, it does have a defined value. There's no jump or asymptote or point discontinuity. So at x equals -1, this function would be continuous but not differentiable. If there's a jump or point discontinuity, remember that's discontinuous, not continuous. And so for C, neither continuous nor differentiable. Well, that would be this jump or this point discontinuity, because our derivative doesn't exist there. We already established that. And because there's a jump or a point missing or dropped, however you want to phrase that, those would be discontinuous as well. So at x equals 0 and at x equals 2. So here we can see that even though differentiability implies continuity, the reverse is not true. If I say it's continuous, it doesn't necessarily mean it's differentiable. Just like in item B here, at x equals -1, it's continuous but not differentiable. So it doesn't work both ways. If I say it's differentiable, it's continuous. But if I say it's continuous, it doesn't necessarily mean differentiable. And that's your introduction to differentiability.